Hey, Neil.
Hey, Eden, we'll start shortly. Just a moment. Can you all hear me? Kyle, Aiden?
Yeah, I can hear you.
It's in person at the Engineering 2 building, right?
I'm sorry?
It's in person at the Engineering 2 building, this meeting?
Yeah.
I'm pretty sure all the Engineering 2, like, all the doors are locked. I'm outside right now.
Oh, if you use your key card, you should be able to enter. Otherwise,
Alright.
come down and
Okay, I'll try that.
I can get in if it's stuck.
I just tried with my key card. It doesn't work.
okay, hold on, I'll come down then.
I got it.
It's fine.
Yeah. Wait, we got it to open. Oh. Dude, you already went down though.
Are we going to okay?
Yeah, I guess so. Are you Kyle?
No, I'm Alex.
And I'm Alex. Aiden? I'm Mark. Yeah. Alex?
Are you part of the instructors or one of the people?
I'm undergrad. I'm just a junior transfer.
We're both freshmen.
Oh, yeah?
Yeah.
Okay.
You'll have your laptops. We'll just try to get familiar with the environment of Hummingbird and submit jobs, compile applications. One good thing about being on campus is we don't have to use the VPN to access Hummingbird.
You sure?
Yeah, I just connected without the VPN.
I think it depends on where it might work in the engineering building,
Okay.
but for EduRoam, I almost always have to log in on the
Oh, okay.
yeah.
Hey Kyle, can you access Hummingbird?
Let me see.
Yeah, just can you log into it, please? We'll start our work there. So. Dayton Alexander, have you been able to access Hummingbird?
I have not.
Okay. Can you try that?
No.
Do you know how to SSH?
Yeah, but I don't know like any like key.
So it's a little bit tricky. You probably have to set up Duo if you haven't done that.
I think you still need the VPN. I use it.
Okay.
So can you send me the download link for the Cisco?
I think I have the
So if
VPN
you search
installed.
Hummingbird, UCSC Hummingbird, the Cisco link is in that first like home.
Oh, you have it. You got it.
Oh, you have it?
This one, right?
Yeah, you need that, and you need to set up Duo as well.
It's the same deal as your UCSC,
Oh,
so
okay.
you should already
I
have
don't
it.
even remember what the heck it was.
The thing is, you have to
No,
you have
you're-
to set up the push thing, and
Yeah, I connected before.
oh, okay, there you go.
You have to phone.
What do you guys use to write code?
Well, right now we're mostly doing Python. We did Python last
BI.
quarter.
Oh, nice.
He's doing CC 13 right now. I'm doing 12 and 16.
Oh, yeah, yeah, that's cool. But like on Hummingbird, do you it's like Putty or
We haven't
Nano?
used. I haven't used. I don't know about him.
For no, Windows has SSH installed.
Yeah, yeah, yeah. I'm using like Visual Studio. This one I'm using like Putty
yeah.
Can Putty do like file system access or?
or
will be
not
the one you're
really.
using instead of
You can
SSH?
just instead of SSH. Just the thing.
All right, so how do I log in and connect to the VPN?
Okay.
No,
Just
no, it's not logged in.
whatever is your terminal, just use that. Do you use this is when you have a Windows installed?
Yeah,
Okay. So you have Putty?
I have SSH.
Sure. Any terminal will work.
Okay.
Yeah, and the terminal, the address would be hb.ucsc.edu. hb.ucsc.edu. The username would be your cruise ID. and
That's
clusters.
that you passed me to. Yeah. Hold on. Yep, you're in.
All right.
Okay.
And was this specifically configured for us to access or can
No, this is the campus-wide sort of cluster. It's a so this is just for today's or probably this month's experimentation. Just so that you get you understand how a cluster is set up, how to run applications on these clusters. Once you're familiar with this, we can create accounts for you on the large supercomputer at Berkeley, and yeah, we can do much deeper experiments there.
And where's Hummingbird located?
I don't know which some data center here, but it's heavily used by the life sciences, the bio departments, genomics departments. But as students we can use it. So like let's see. So this is what you should be seeing, like at HP. Just a moment. Arshan, do you have access to Hummingbird?
Can you say that one more time?
Do you have access to the Hummingbird computational cluster at UCSC?
I don't believe so. No.
Okay. So just paste the link in the Zoom chat. Can you try to follow the instructions here and log in, because that's where we'll be doing our experiments today.
Okay, thank you.
Yeah, it shouldn't take you much time if you have like the Cisco VPN installed and if your Duo multi-factor authentication is set up. Okay, so let's see, this cluster, some details about the cluster. Currently it has 500 Intel CPUs. So that's the entire system. So how the system generally is like, you'll have something called a node. Okay, that's as a programmer, for your experiments, that will be your basic building block. Whatever job you run, it will be running on a single node or multiple nodes. So in this cluster, one node has 44 CPUs, as you can see here. So one node is 44 cores or CPUs and has 256 GB of memory. Okay. There are some other nodes.
RAM memory?
Yeah, RAM. Yeah, these are pretty dense nodes. Yeah.
Total, how much does the whole supercomputer have?
So that's what, let's see. So there's one node which has 256 GB. There are 19 nodes which are 24 CPUs and 128 GB each. So you can see it's probably like it's just close to 2 terabytes here itself. Then you have some AMD CPU, some nodes with AMD CPUs. So 2 nodes with 192 GB and 3 nodes with 256 GB of memory. And there's also a GPU node, but we are not focusing on that right now. But like just to give an idea of the clusters, how powerful and these systems are. Like these are some specs. Now to actually see how these nodes, like how these nodes are configured and all. If you go to your terminal, one way to see, so there's like a software manager for normally in a cluster setup. So as a user, when you log into some cluster, you log into something called the head node or the login node. It need not be just one node, it can be multiple nodes depending on the size of the cluster. So like this one has probably just one login node. But if we compare this to the supercomputer at Berkeley, which is like in probably it's in the top 5 most powerful supercomputers in the US or in the world actually. So it'll have like 30 login nodes, because at a time you'll have thousands of users who are tens and thousands of users are trying to access that supercomputer and run jobs. So here, this is whenever you SSH to a supercomputer, you log into the login node, and you use something called a software manager. or a scheduler. So what it enables you to do is to run jobs. So the thing, why would you need such a scheduler is, so let's see, if this one has like 20 nodes, right? Hummingbird has like some 20 separate nodes. And if four of us are trying to run jobs there, how would we schedule, the who runs on which nodes and, how much time is allocated to each user, so on and so forth. So one way could be that all four of us communicate with each other and decide something that okay, let's say Aiden wants to run it on like 5 nodes, Alexander wants to run it on 5 nodes, Mark wants to run it on 10 nodes, and you know so all 20 nodes are distributed amongst the three of you. Now if I want to use, I have to ask you guys like how much time is your job going to run for, how much time should I wait, so on and so forth, which is pretty cumbersome when you have like tens and thousands of users. So you have this scheduler, which is like essentially like a queue, right? Okay. So as users submit their jobs, it gets put in the queue, and based on the availability of resources and some other metrics like okay, priorities and so on and so forth, the jobs are automatically scheduled, and that's the responsibility of the scheduler. Now, apart from running these jobs, the scheduler is also responsible for like telling you about the nodes of the system. Because if there are like 20 nodes in your supercomputer, and if you want to check how many nodes are free, how many nodes are busy, what's the health status, sort of system status of these nodes. If there's no software sort of manager, software scheduler looking at everything at the same time, you would have to probably individually check each node, which is again a lot of time waste, right?
Is a node like a group of hardware, part of the whole machine, or is it
So
some
a
kind of
node you
software?
can consider like one system. So it can have a lot of cores, but it's like a single entity. That's the basic building block of a supercomputer. So you can, yeah, it is possible for multiple applications to run on a single node, but for HPC and for these competitions, you can assume that at a time, only a single user is running any application on one node. So, that's how nodes are used. Like that's how the term nodes is used. It's like
Can you use one application running on multiple nodes?
it's, so we'll go on to that, but the basic building block is one node. I don't know if is the whiteboard visible. Is there some way to change it? Let's see. I can use this to show the whiteboard for others. Yeah, I'll just draw the architecture there so that you can visualize it better. Let's say this is Hummingbird, okay? So this is like, this would be the Hummingbird data center. Let's assume that's how it looks, okay? It's a huge room filled with servers, okay? Servers would be these tall racks, okay? So let's say this is one rack, two rack, three rack. Let's assume there are 5 racks, okay? The actual thing may differ, but for now, just use this as an analogy. So this is a rack. each rack has the nodes. So the nodes are a part of the rack. They're positioned in the rack. So let's say Hummingbird has 20 nodes. And since there are 5 racks, each rack has 4 nodes. Okay, so this is a rack, and this is a node. Okay, so and all these nodes are interconnected by a high-speed network. Now, Hummingbird is a bit old, so it is not the latest and greatest high-speed networks, but typically in a HPC supercomputing center, you have something called like an InfiniBand network. So this is like much faster than a typical Ethernet, something that we use to access the internet. So if our Ethernet is like I don't know 100 gigabits per second, this one is in modern the modern speeds of InfiniBand are like either 200 Gbps or 400 Gbps, like depending on which type of network adapter you're using, and that's on one adapter. Now, in when we access the Berkeley supercomputer, you can look into it, but it is possible for one node to have multiple adapters, so the overall bandwidth can be much higher. So if one node has like 400 Gbps, then you can get like 800. The theoretical limit is 800 gigabits per second of network output. So yeah, the just some details about what InfiniBand is and how it is different from the Ethernet connection. So what InfiniBand does is something called DMA, that's direct memory access. Like this is one of the things which makes InfiniBand faster. Like there's just some background, just so that if you want to read up more about it and you encounter these terms, you know that you're on the right, you're using the right source of information. So what the DMA helps you do is directly access the CPU memory on any node. So one node, let's say this is a node. Normally, supercomputer systems have 2 sockets in a node. This is a socket. Okay. And each socket has the CPU. This is the CPU, which has like lots of cores. Guys on Zoom, so in case, yeah, you can see this on my, I'm sorry, I didn't specify it before, but I'm writing something on the whiteboard, and you can see it on my webcam. And do tell me if it's not, visible to you. But yeah, so this is like, before going to network, let's look at this. So there, the supercomputing center has a rack. Each rack has nodes. A node can have one or more than one, typically 2 sockets, and each socket is the CPU. So what this CPU is like what we have on our laptops. Our laptops will have probably like 4 cores, quad core, 8 cores, 2 cores, depending on how old or how new the laptop is. Whether it's a Mac, Windows, doesn't matter. The number of cores are typically less than 10 cores. But there are different types of cores. Like Mac has some different design, and our AMD Intel cores are a bit different than Mac. But essentially, you can say that each of our laptops have less than 10 cores, and supercomputing nodes have like lots of cores, which implies it is mostly 20 plus cores. per socket. Okay, normally like it can differ, but normally it's 20 plus cores per socket. So that means each each CPU has 20 cores, let's assume. So one node, because there are two sockets, one node will have 40 cores. Let's say 40 plus cores. So and each core can is like can be used to run an application, and that's what makes it sort of powerful. That you have something. The idea behind supercomputing is something called parallel programming. So the idea is that if you have a large enough problem, it could be simulating like airflow over windmills or aircrafts or cars. It could be like modeling the next COVID vaccine, some other drug. It could be, as we discussed in that session, it could be video rendering for Disney movies. It could be whatever, some training some AI model, whatever. The idea is parallel programming, or that the problem is of such a format that it can be divided into smaller chunks. Okay, so and the advantage of dividing into smaller chunks is that each individual core can work on that chunk. Sorry, yeah.
Oh, so we're thinking about like parallel cores, right?
Mm-hmm.
But are we ever going to write programs where we have parallel nodes?
Yeah.
Oh, okay.
Yeah.
Like, what's an example where we would use that kind of thinking
All of these examples.
with nodes?
Yeah.
Okay.
So that's where this network comes into the picture.
Yeah.
There's some connection between these cores as well, these two sockets as well. But I'm trying to build up to that, and yeah, it's good that you're asking these questions so that I can I'm sort of just speaking out loud. This is not yeah. So based on the questions that you guys ask, the conversation will that will steer the conversation. But the idea is, if the problem is very large, you can either take your laptop and spend years to solve that problem, or you can divide that problem into small chunks and use like thousands of laptops, each individually solving a different part of the problem to solve the entire thing. So that's the idea behind parallel programming, and that's what happens in a supercomputing center. Is that if the problem is large, if the problem is large enough, you can use all of these racks, all of these nodes, all the cores inside these nodes to solve that problem. So that's where this parallel programming is. So one, as Mark said, that there's two ways to look at this parallel programming or the solving aspect. One is parallel programming. One is, say, intra-node. One is, the other is inter-node. This is inside one node, and this is multiple nodes. Now, any problem that so for both competitions, whatever application is given to you, you start with intranode, or you start with running the application on a single node, and you try to normally the idea there is that you achieve the best performance on a single node first, and then use that recipe, use those insights to run jobs on multiple nodes. Now, inside one node, what's the advantage? Can you guess? Like, compared between these two scenarios?
It's probably just easier to, the abstractions, it's easier to keep track of.
You don't have to deal with like having work on assigning work to other nodes and only just having to deal with that one.
Yeah, awesome. So some more caveats in that. So like, yeah, you do still have to, like each node has multiple cores, right? Like you have lots of cores. So you still have to look into scheduling, like how each core is solving the problem and how do you assign work to each core. That sort of scheduling is still going to happen. You do have to do some coordination there, but it is not as convoluted as it would be with multiple nodes. So yeah, you're on the right track.
So you can kind of do the same thing on your own laptop when you do like multi-threading.
Yeah.
Okay.
Yeah, so great term. So intra-node, you normally do it with threads. Softwares that are typically used for this, one thing which is, and so everything that I'm talking here is very HPC centric. So there are multiple other things that can be used to solve the same problem, but whatever I'll talk about, I'll try to restrict to HPC so that we don't keep on talking forever. So in HPC, these threads is achieved with a software called OpenMP.
And what exactly are threads?
So threads, software threads are like you have, if you have like 40 cores on your node, right? You will have one sort of thread or background, one process running on each core, okay? And you can have more than one as well, but right now assume that if you have 40 cores, you have one sort of software process running on each core, and it's these processes have been started by the same application. So let's say you're running an application for whatever, video rendering, okay? So that application launches multiple threads or software processes, whatever. The terms in our conversation can be used interchangeably, but actually it could be like, these processes versus threads is like are different terms. But for now, assume, let's say the application launches multiple threads. Each thread is doing the same thing. You have a big problem, it is trying to solve some part of it. On each core, you have one thread. Each core is trying to solve a different part of the problem. And since one application has launched these threads can talk with each other, so that and that communication is necessary because not all problems can be solved like like it's not very easy to divide a problem such that you can make it like in a way that each thread can do it in a bubble. That's not always possible. So this is called something called embarrassingly parallel. So if something is embarrassingly parallel, it means that you can just do it like each thread can do it individually without any communication with each other. But having embarrassingly parallel problems is like in the real world is not always true. So one example for this could be like if you have a large array, okay, some large integer array, and you just want to add one to each element, okay? So plus one for each element and generate a new array. Now, since you're adding one to each element and it's not affecting like, the addition or the operation on one single element is not dependent on any of its neighbors or any other element in the array. So in this case, you can do it like, this is an embarrassingly parallel application example because suppose if you have 40 threads, each thread, let's say one thread says, I'll choose this, the other says this, so on and so forth. Each thread can say, I'll access one element from the array, I'll add the number one to it, and I'll write it in a new array, or I'll write it in the same array, whatever, based on how you program it. So, in that case, it's that this is an embarrassingly parallel thing, and this is what supercomputers are, or actually not just supercomputers. This is something GPUs are very good at. So the as you saw here, cores, multiple cores. GPUs have like thousands of cores on a single GPU. Nowadays, 5,000, 10,000 cores, probably 8,000 cores, something like that. But those cores are lightweight. CPU cores are pretty powerful. They can do complex, they can execute complex instructions, so on and so forth. They have powerful, they can do tasks quickly compared to a GPU. GPU cores operate at a lower frequency than CPU cores, but since you have 8,000 cores, and if you have a large array where you're just adding one to each element of the array, just because of the sheer number of GPU cores, you can do it faster than a CPU. But that's again, very application specific, which is why things like video rendering, games, AI, GPUs are very good because the kind of mathematical operations that are happening in those applications is more or less embarrassingly parallel. So if you throw a lot of cores at it, and if you have written your algorithm, if you have chosen algorithms in a way that it's embarrassingly parallel, GPUs will always outshine CPUs. So yeah, this is an example of an embarrassingly parallel thing. A counterexample which makes it difficult for single threads to do it in a shell is, let's say you want to get something like the average of this array. Okay, and average would be just summing up all the elements divided by the number of elements, right? Now, actually, no, that's not a good example because I could do a divide here. But some other mathematical operation where, okay, average in a different way. Let's say I want each element to be replaced by the average of its neighbors, or like of a window. Like let's have an average in windows. Okay, so let's say this needs to be replaced by, even this is embarrassing parallel if you think about it. Like let's say this needs to be replaced by the average of 1, 2, 3, 4, 5, like 5 itself, and two neighbors on its left, two neighbors on its right. And you do this for all elements in the array. Now, since there is, like, you are looking, actually even,
Are you trying to show us an example of something that's not embarrassingly parallel? Okay.
but still parallel, but not
But still
embarrassingly
parallel.
parallel. Yeah.
Okay, that's
But the idea is if there are operations which depend on the intermediate results of other threads. Okay, the assumption here is each thread is working on a single element of the array. If there is some operation which depends on the intermediate results of the other threads, you would need to have the threads communicate with each other, right? Otherwise, it's no longer parallel, because if each thread is going to work on, like, you need to have that communication to get the information about the neighbors. Okay, so whenever that happens, it's no longer embarrassingly parallel because the threads have to synchronize, have to send and receive data from each other.
for threading. That's when we would do the. There's a thing you call. It's like sync or something.
Yeah.
Or like catch, and then it like waits until they all get to that point.
Yeah.
Yeah.
So
I forget what it's called.
synchronization is
It's something. It gets used a lot in a bunch of different languages.
Yeah. So you put a barrier and you wait till all threads have done their intermediate computation and interchange results. But that's an example of a parallel application where you need the results from other threads as well. And when that happens, you need some way for the threads to communicate with each other. And that's easier to do in a single node because you're in a single system. The way these threads since all these threads are like either on the same CPU or in a neighboring CPU, the communication speed is a lot faster, and it's more reliable compared to this network. Like when you use, so all this communication here is happening on the chip itself, right? On the silicon level itself. There's no physical wiring connection from here. Like normally these are interconnected by wires, right? So once there's wires, there's reason for like the wires failing or congestion, so on and so forth. But like here, inside a single node, they normally use silicon as the way to communicate with each other. So that's a lot faster. But like, yeah, this is just a bit of background. But the idea is, sorry. Okay. Yeah, but the idea is for these computations, you start with optimizations on a single node, and the way to do those optimizations is like, yeah, you try to use OpenMP. Now, these competitions are like you don't have a lot of time, so it's not like you can write your own OpenMP. Like you can't make an application. You don't have enough time to make an application support threads if it does not. But normally, the applications that are selected for these competitions are pretty well used, so they will natively support threads. You just have to know how to run these applications with these threads, find out if there are any bottlenecks, and figure out how to resolve it. So programming is not the number one thing that you will do here because of the constraints of time. I mean, if you have time to devote, and if you compare the two competitions, the Winter Classic is like you are focusing on one application for 1 week, and then you forget that application and you get a new application. So in that 1 week time frame, you have to compile the application. You have to get some base results, like just after compiling, you have to figure out how to optimize it, and then give the optimized results. And also, step 0 would be learning about the application. So this is these 3-4 steps are themselves very time consuming. So programming the application would be even more time, but we can teach you that if you want, but it's all up to you guys what you want to do. But yeah, the idea is that you first try to optimize the application for a single node. For that, you need to optimize how threads are being used by the application. So yeah, let's see.
When you say we're given an application, do you mean like we're given the source code and we just compile that?
Yeah.
And like maybe there's like a module left out or something. We need to fill that in there.
No, you don't have to fill any modules. So let's see. Let's talk about.
I'm just kind of confused on what the goal is, I guess.
Sure. So I'll talk about ISC because they have released like the problem statements for that. So for ISC, it's like they have released released the names of 3 applications.
So do we work with all of these, or?
Yeah.
And that's just like we work with one, and then that's over, and then we work with another one.
No, for ISC, it's like you have 2 months to do whatever you want to do.
Okay.
So there's no windows for these applications.
Oh.
We can start. We have to start the optimization efforts now itself, so that when we get access to these nodes, to the ISC nodes, we can get started and do as much optimization as possible on them. So there are 3 applications for ISC: Quantum Espresso, Pot 3D, and UTAS or something. Yeah. So these are open source applications. Normally, HPC is a very open source oriented community, except maybe automobile engineering, which has a lot of license based applications, but most of the other domains are open source. So these are 3 applications for the ISC competition that they've sort of announced. We are supposed to download the source code. Step 1 is download source code. Step 2 is build the application. And 3 is baseline results. Run the application essentially. Okay. Now, these applications are going to be like, compared to what we are talking about right now, these applications are a bit more complex. So they depend on multiple libraries, they depend on other software to make the computation faster. So these other softwares can be like specific linear algebra libraries, which are fine-tuned for a specific algorithm that the application uses, or some systems library like for storage, for like if the application is using a specific, the data set of the application is in a specific format, and you want to improve the speeds at which you read and write that data, you can use another library. Other libraries would be like the choice of compilers that you use to build these applications, the choice of library that you use for internode communication. That's called MPI. So let's use it. So internode, you do that
So you
through.
have to find these applications and install them.
Yeah, they have given the links already. They'll give that, they'll do the initial part. They'll tell you the name of the application. So for the Winter Classic, based on they haven't updated their website the last time I checked, but based on the previous participants and their feedback, so they will have like either the developer of that application or some well-known expert from that application. Okay, they will conduct an initial session where they'll talk about the application, what it does, how to give some ideas about how to build it, and probably some more hints about the application. So they'll give you the source code or the link or the GitHub repo where the application is. They'll tell you for this is for the winter class, okay? They'll give you the GitHub repo. They'll tell you about how to build it. Some hints about the application characteristics. Your job would be to build it on the system, whatever that competition has arranged. They will. Last time they arranged some Google Cloud servers. This time we don't know what it's going to be, but it'll be some supercomputing center. So you have to figure out how to build that application there, and get baseline results. This would be the first step. Once we have baseline results, we have to figure out ways to optimize that, and that optimization can be done in broadly two ways. So we can call it runtime optimization or compile time optimization. It's compile time, and third would be source code modification.
How would we change the runtime or compile time without changing the source code?
I'll tell you about that. So you won't change the in runtime and compile time. It's not changing the actually. Let me tell you about. So applications have many HPC applications have tunables which you can set at runtime. Let's talk about Quantum Espresso. So in Quantum Espresso, from what I recollect, you can set. There are a lot of parameters which are directly related to the underlying algorithm, which you can tune at runtime. And it's all based on since you may be familiar with domain decomposition and things.
No.
It's just a fancy way of saying how the data set is chunked into smaller pieces.
Yeah. Okay.
So we normally assume that the problem size or the problem that we're trying to solve, its structure is uniform. Like maybe it's like this is the problem size, and let's say we chunk it like this.
Mm-hmm. And you mean this like computationally or like how?
Computationally.
Okay. Yeah. Okay.
I mean it. When you actually program it, it'll spill over into the other way. But let's say so. Like how? Let's look at this computation, right? Let's say we are trying to do weather forecasting, and let's say this is some region in California. Yeah, and we'll divide the grid into smaller pieces, and let's say each core does the physics simulation for this section.
Mhm.
Maybe like, 1 kilometer, 1 mile by 1 mile.
Yeah.
That's the small grid that we have defined. And each core is doing simulation for 1 cross 1 mile, okay?
Yeah, I get this.
Yeah. This is, in a way, this is what domain decomposition deals with.
This makes sense.
Yeah, this is a very uniform grid, right?
Mhm.
What if
You want to make it smaller or something.
what if this is not how it looks, right? Like, what if it's like an irregular shape?
Mhm.
How do you define a grid here? Like, if you try to do this, like you can do this, like that's how you will start. But what happens in this case is like
Oh, I see.
some, like let's say this one. This will work on a very small part,
Yeah.
whereas this will be fully populated. You may miss out some things if you do not chunk it properly,
Yeah.
so on and so forth.
I get that.
Yeah. So you want to make the computation as uniformly distributed as possible over all the cores and the nodes. So yeah, that's one of the runtime things that you can adjust in some applications. And quantum espresso is one of that.
It makes a lot of sense.
Yeah.
Yeah, we're usually given those like algorithmic parameters where it's like k or some constant or something.
Yeah. So yeah, other runtime things that we can adjust is the library that we will use for internode communication. That's MPI or message passing interface.
So in this competition, we're probably going to be using internode communication.
Yeah, you will use internode communication. That is the main thing that we have to tune and get the best results out of it. Because ISC, it's like we have to submit results for like 1 node, 2 node, 4 nodes,
Oh yeah.
probably 8 nodes also.
There you go.
And the best possible results at such a scale, and maybe even use GPUs. So it's like you have to use 4 GPUs working together. So if these are 4 GPUs,
Yeah.
and how they communicate, and how that's all achieved. You can assume that each GPU is a node. So again, there's some form of internode communication happening here.
And that's potentially going to happen, or do you know that we will deal with that?
GPUs? Yeah, it is. It's part of the problem statement. But if you saw the group, so yeah, they recently posted they may not opt for the GPU part, but they'll tell us by the end of this month. But in the original problem statement, GPUs are a part of 2 applications. So yeah. But like the runtime optimization is for one of the things very heavily, which has a lot of potential for runtime optimization, is the message passing interface library, or how does internode communication happen, and that can be tuned because these like this NPI libraries are pretty general, right? Like they are designed to run on any type of supercomputing system. So depending on the supercomputing center where you are running, okay, I'll come back to that, because for that you need some idea about internode communication. But for now, just consider runtime as either algorithmic runtime parameters or message passing runtime parameters, okay, internode communication. Compile time would be playing with compiler flags, or like trying different compilers.
Oh, so we're not given a specific compiler to
No,
use.
that's all open. That's one. These are the things. Trying different math libraries, trying different compilers.
Are we given like a base, linear algebra library that's going to like get everything working?
So in there, normally these applications are open source, right? So they will have like a README where they'll talk about that. Okay, this is what we have tried with, and they'll have like make files for some experiments that they have done. So we can get that started with that for the baseline results. But like this is an open exploration thing.
Yeah, it's a lot.
Yeah, and source code modification is normally not a focus area for these competitions. It's just that if you know something that can make, and you can put it in the, we can put it in the solution, in the proposed whatever solution that we send to them, and it may help you, get like some special commendation for like extra efforts that you've done from the developers, from the organizers, that sort of thing.
That's interesting.
But because this requires a lot of domain expertise, right? And normally, like as students, as computer science students don't have it a lot. Applied math students have studied those algorithms, so they are much more, I guess, in a better place to start working on source code modifications. But like, yeah, it's also dependent on time. So
Yeah.
but
Just
then,
what you
yeah.
described is a lot of work.
Yeah.
Like,
Yeah, so the same holds true for the Winter Classic, that you will have these 4 steps to do. And it's not like, I know we have talked about a lot of things, but you don't have to, don't be like, it's the field itself, the field of scientific computing is like that, the optimization, it's a never ending, it's a never reach, it's a goal that's not reachable. Like you'll always find some or the other way to optimize something. So don't worry about that. We'll sort it out together. But like, yeah, this is a bit about the competition. Spend an hour, right? Okay, good. I'll talk about internode again, but before that, any other questions about things that we discussed? Do you want us to go over some of the topic that we discussed earlier?
Maybe like how do we deal with internode or inter-rack communication?
Yeah, I'll talk about that now. Anything apart from that, Aiden? Yeah, cool. Okay, so inter-node communication, right? Once we go outside the node, like when we have multiple nodes working with each other, how does that happen? InfiniBand is the basic connection there. So it's like, yeah, these are very high-speed networks. There are different type of cables. They are not these fiber optic cables, or they're like pure copper cables, very thick. A lot of them coaxial copper cables that are used.
What's like the protocol? Is it like TCP or is it something?
No, that's what DMA. So what DMA does is, so TCP is like a stack, right? You have all those layers, application, network, blah, blah, blah. I don't know all those terms, but like you go through all the layers before reaching the actual application that is run on the CPU. And like the TCP involves all those layers. What DMA does is it bypasses all of this. So if essentially you bypass the operating system and whatever is running in the operating system, and directly access the kernel, directly access the application and the memory which is there on the CPU memory. And that, since you're bypassing so many software layers, so many abstractions, you get very high speed ups.
Accessing the CPU cache memory or the RAM?
RAM memory, cache memory, whatever. It's
Well, like the memory that's built into the CPU or that's detached from the CPU?
both things. So normally it's the RAM memory, which is, if this is your CPU, this would be a RAM. So normally you access here, but you can find ways to play around with the cache memory as well.
So from one node, you can access any other node's memory?
Yep.
And what kind of software do you use for that?
Message passing interface, MPI libraries, all out there. UA is not here. She may have better. But yeah, the idea of message passing interface is that you rely on something like this to make communication faster. And what it does is, so the way these systems are configured is, let's see, if you have the network card, I need some more space for this. use this. So one way to look at this is there's something called PCIe, which is like the interconnect inside a node, okay? And you can have like the CPU talks to the other components like the network adapter or RAM through the PCIe channels. And because InfiniBand is connected to PCIe, it can directly read or write things into the RAM. And this is one node. Say you have another node like this here. So if you have CPU, RAM, InfiniBand, so you have PCIe. These are connected. And since they can talk, this via this adapter can read something from this RAM and vice versa. And you essentially bypass the CPU. You bypass the CPU and bypass the operating system and the software layers and directly access the RAM. That's DMA. This is called RDMA. There's an R also if you want. That's remote direct memory. This part is RDMA. This is DMA. Inside a node, it's DMA. Outside, when this thing is RDMA. But yeah, this is what makes supercomputing networks high speed, very fast. And yeah, NPI allows you to do that. Normally, how NPI is, now we're talking from as a user, as a developer, as a software user. NPI is like a separate library that we use, which can integrate with whatever compilers that we can use. Okay, so I'll remove this domain part. Just talking. After this, we can sort of look into the hands-on thing so that we can see these things happening. So compilers that are available on most systems, the default one will be GNU, which gives you access to GCC as a C compiler. So, okay, before that, most HPC applications are written in C, C++, or Fortran. Okay, so yeah, so with GNU, you have GCC for C compiler, G++ as your C++ compiler, G Fortran as your Fortran compiler. You also have vendor-specific compilers, like based on whatever that they normally put in some software optimization so that it can run faster on their CPU, right? So Intel has its own set of compilers, maybe like ICC, ICPC, and iFort. What else is there? You have LLVM, which is like a different set of compilers, which is more geared towards interoperability between different types of. So if you want, so normally what happens with these applications and compilers, right? So if you are building something for, let's say, an Intel CPU, okay, and if you want to run it on an ARM CPU or an AMD CPU, Intel AMD may work because they share the same instruction set. That is, they're built on the same architecture of x86 64. But ARM is on a totally different architecture and ISA. So that interoperability, an application that you build for Intel cannot directly work on ARM. You'll have to rebuild on the ARM CPU. What LLVM is trying to do is give you this interoperability. If you use the LLVM compiler, you will have some intermediate representation. Are you guys familiar with Java?
Yeah.
Java operates on a similar fundamental, right? So when you
Line code or whatever.
yeah, bytecode, that's the intermediate representation. So if you write some code, when you compile it, normally what happens with C, right? If you do GCC compile and you get an out file, right? A .out file, which is the executable that you run on your system. Now that .out file is very system specific, or right, which depends on whatever is the chip on your system. So if you have something which you have built on, let's say a Mac, and if I use that .out file, it need not run on my Windows laptop. It may run from one Windows to another laptop, to another Windows laptop. That's possible. But with HPC, it's not like there are so many other compiler optimizations that we use that something that is optimized for one HPC system need not be optimized for the other one, because there may be architectural differences, like CPU architectural differences. Like let's say we are compiling something on Hummingbird, okay? Hummingbird is an older generation of Intel CPUs. So whatever compiler optimization that we do there, fine, we have an application. Let's say we take that executable binary and we copy it to the Berkeley supercomputer, which has like the latest Intel CPU. It can run there. It may not run there. Both things are possible, but more or less it will run there, but it will not be the fastest run because it has been super optimized for the old Intel processor. And yeah, in order to get the most performance benefits, like our target is performance, right? So we have to extract it as much as possible from wherever possible. And yeah, because of that, you will have to more or less rebuild on the new supercomputer.
Are there places where it's not allowed in the competition to extract performance, like explicitly?
Extract performance, right?
Just like, I can't really think, like maybe we're given a data set and like maybe going through the data set and like reorganizing it or something, that'll get us performance. It's like, is there anything that's explicitly not allowed?
Yeah, some things are not allowed like that, like as you said,
Oh,
pre-processing something to make it easier for that particular,
yeah.
data set. It's a thing that we can add as suggestions.
Yeah.
That okay, well, we found this way.
I wouldn't expect that to like add any performance, but like
It does actually.
Yeah.
Like especially for like some applications which have a lot of like reads.
Yeah, that's true. Yeah, that's true.
If you find some way to cache that read data, or arrange it in a format which is very very fast to read, that can give you substantial performance benefits. But then that is not something that is applicable for everything, right?
Yeah, exactly.
Yeah. The other things that you find out normally, like compiler, runtime things, that is more representative of the actual application characteristics. Yeah. So yeah, it's in these competitions. I mean, the last thing that we participated, they haven't mentioned anything like this, that they haven't restricted anything like that you can't do this, you can't do that, because normally people don't have enough time to reach that stage.
That's fair.
Yeah, there are a lot of stuff here. But if we have such ideas and if we can work on it, if we can find it out, it's always a great thing to add in the report. So yeah, there's Intel, there's LLVM, which is like Flang, something. Now there's AMD compilers as well, so on and so forth. So there are a lot of compilers, and not just that, there are you have different versions of these compilers. So let's say, which depends, like the default GNU compiler would depend on what type of Linux is installed on the compute nodes. So these are compute nodes. So that's another terminology that we use. When we log in at HP, that's a login node. Let's say show this thing. S info. This is a Slurm command which shows you the types of nodes that are available at the Hummingbird Supercomputing Center. So we are at HB. We are at HB. Okay. That's the login node. That's the host name of the login node. These are compute nodes, HB, COM, 000, 001, 002, 003, 004, 005, so on and so forth. So this info is from the software scheduler that we talked about initially. On this system, it is called Slurm, S-L-U-R-M, Slurm. And yeah, it does the task of running jobs and monitoring nodes. So it gives you these information, right? Like you have 5 nodes which are free, and those nodes, the names of those nodes are these. You have 13 nodes that are in a mixed state, and these are those nodes. Now, what could mixed state be? Let's see if some jobs are running. That's SQ. This is the queue of all the jobs that are either in the queue or are running. Now, if you see here, like the different fields, you have the job ID, you have the name of the user who has launched the job, what state it is. R means running, how much time it has been since the job started, what node the job is running at, so on and so forth. Let's see if I put a job. Okay, let's say I'm running a job. If I run SQ again, yeah, do you see the last one?
Yeah.
Yeah, that's that's me. I've gotten my jobs running on this particular node. It started 8 seconds ago, or whatever. And so this is how you see the system when you run a job.
Can you talk about the partition?
Sure.
Because I noticed you left it as instruction, but there's also an option for partition.
Yeah. Just cancel the job. So partitions are a way to group nodes on the system. So these are the partitions. Okay. Now, as we saw on this Hummingbird site, you have different configurations of nodes, right?
Mhm.
So you have one node which is 44 cores and has 256 GB of memory, but you have 19 other nodes which are 24 cores and 128 GB of memory. So what this means is like you have 44 cores, which means it's a particular CPU SKU, like Intel 6 one, some random, a particular chipset. These 19 nodes with 24 cores are a different chipset.
Oh, so that's like these are like a classification of nodes.
Yeah,
Okay.
but it depends on the admin how they group nodes.
Oh yeah.
Yeah.
But in this case, this is how they're grouping.
Yeah. So they are trying to group nodes. So like if you see here 256 cross 44, that's that first node which is 256 GB and 44 cores.
But you're not getting all those cores. You're getting all 44 cores.
Yeah, I'll show you. Hold on.
Oh wow.
So that node is idle, right? Let's see. I'll do an slloc. So slloc is the way to run. Okay. Let's say the partition is from instruction. I'll change to 256 x44. One node, 1 hour, one task, exclusive. Exclusive says that only I can access the node.
Okay.
And I've gotten access. Let's see. SSH. So I am on that node now. HBComp 005. Yeah. And I'm on that node. And let's see. So ls CPU will tell you about what kind of CPU this system has. So it has an Intel E5-2699 V4, and which has 22 cores per socket and 2 sockets.
Oh yes, the 44.
So that's the thing, 22 cores per socket, 2 sockets. So you have 44 cores per node. And
Sorry, there's also an option to like specify the cores as well, or maybe I was misreading that.
cores like,
You can say like 4 cores or 6 cores, or
yeah, you can do that.
what happens in that case?
So normally what happens is when you you will probably get like it will not turn off code. Like it is possible to turn off cores as well, but normally we don't do that because it takes time. Yeah. So what rather happens is when you launch jobs through the scheduler, right, through Slurm, and if you have requested only 4 CPU cores, and so when you launch the job through the Slurm, it will only launch your job on those 4 cores. Even if there are 44 cores available, it will limit your job only to 4 cores.
But it doesn't like, allocate those cores for other people.
So if you say exclusive,
Yeah.
only 4 cores will be available. Those 4 cores will be available only for you. Nobody else can run on it.
But will the other 40 cores, will they be available for other people, or is it just like
if it's exclusive,
Yeah.
that means the entire node is for you.
entire node? Oh wow. Okay.
But if it's not exclusive, those 4 cores will be for you, and somebody else can use the other 40 cores. But so that's the CPU information. With free, you get idea about how much memory there's available. So there's like close to 256 GB of RAM,
Yeah.
which is there on this node.
You can do a similar thing where you ask for a specific amount of RAM, and it's the same case where it's like that's not going back to the network. It's just like allocated because it's a node.
Yeah.
That's interesting.
So with RAM, I'm not very sure about how Slurm operates for like a RAM limitation. It could be with it will be some sort of software limitation. It's not a hardware limitation. Like it's not like the hardware is not changed. The hardware configuration of the node is not changed. It is a software limit that says, okay, your application can only run on this much amount of RAM. But again, that's not these options are not heavily used by HPC for our competition because we want performance.
Everything. That makes sense. That's interesting.
Yeah. So
And when you just say the partition is instruction, that becomes like an interactive session?
no, I think the way they have designed this cluster is then some nodes are in that partition, instruction partition, which are like less powerful and less used for the actual simulation runs.
Interesting.
So that's why they've kept like 5 nodes for that, so that for these teaching sessions, let's give them more time. Otherwise,
I was using those for compute, so
I mean, they are compute nodes.
Yeah.
But it's
like
not
a lot
like
of
we are. Yeah. But currently, we don't need a lot of compute. So okay, so these are some instructions that you should sort of just use for the scheduler. So if you want to read up more, put something. I can put it in the chat so that folks on the chat can read up on that as well if they want.
We can put it in the Discord.
Sure. Otherwise, if one of you can put it out there, it'll be. So you have Slurm scheduler and some example. These commands are sinfo for cluster system information. You have sq like jobs running. Or in queue. You have salloc to allocate a node. We also have something called dispatch, which we will use today for batch submission. And what batch submission means is like you can submit nodes in jobs in a batch. Like let's say I want to run 5 different types of jobs or one job 5 times. I can submit everything in the queue, and the queue can the Slurm scheduler can take care of it. I think I'll limit the whiteboard stuff today to this much because this is a lot of info. But in this current information, whatever we have talked about today, is there something else do you want me to reiterate or cover more?
I'm not exactly sure about compilers and compiler flags. What are the?
So I'll talk very briefly about compiler flags because we can talk about it in the next session because it's another level. A lot of things to cover there. But these different are you clear with the different types of compilers that are available to us?
Sort of like there's just different types.
Yeah, there are different types. For now, let's keep it at that. We have different types of compilers. Now, these compilers can optimize your source code and the build, the final build, the executable in different ways. Now, these optimizations can be of something called architecture-specific optimizations. So let's say I know that I have a particular Intel CPU, and I know the inherent, because we have the model, like whatever Intel chip is there on the compute node, we can look into the specifications from the vendor about that CPU. We can understand that, okay, some characteristics of that CPU. So there's something called vectorization, which is a very heavily used thing for HPC. What vectorization allows you to do is run multiple. So this is a very small, like let's go back to the array example, okay? What vectorization allows you to do is rather than like accessing one element at a time, you can access elements in a chunk or a vector. Instead of a single element, you access a vector of elements, like a certain, and that's some functionality which was added to Intel CPUs, I think, 10 years back or something. But like in 2005's, 8's, when vectorization started becoming popular. And so normally our CPUs are 64-bit, right? Which means that you can execute instructions which are 64-bit in length. Or your data bus is also 64 bits, something like that. But what vectorization allows you to do is you can combine these like 64-bit, you can make a larger length vector out of it. So suppose your Intel CPU supports 256-bit instructions. So it can combine 64 into 4 and operate on data which is like 64-bit into 4. So like 4 chunks of 64-bit of data at a single time with a single instruction, rather than waiting for 4 instructions to operate on 64 bits individually. You can operate on everything in a single chunk. And that's very good for performance because you can do things faster. But I'll cover these topics again, vectorization. But for now, yeah, vectorization is something which is very heavily used by HPC and which is very architecture specific because it depends on what family of CPUs you are using. And that is something that you control with compiler flags. You can enable certain optimizations, like these vectorization related optimizations. You can enable things like compilers use things like loops, right? So loops are very specific in computation, right? You iterate over certain elements. Now, how you iterate over those elements can be controlled with like compiler flags. So for loops, rather than, again, vectorization can help you there, rather than accessing like for I from something to something, rather than accessing one element at a time, And let's say if you're running that for loop for 10,000 elements, rather than running it 10,000 times for a single element, you vectorize it, and let's say you operate on 256 elements at a time. That is one way you can do that. It's called like loop unrolling. So if the loop is 10,000 times like this, why don't I unroll it a little bit? And let's say 256 times until I've reached the final count of 10,000. You can control that with compiler flags. You can control the precision of your mathematical operations. So HPC operations are floating point, right? They are in floating point because you work with decimals and a lot. So, but you can't represent our decimals are to the part we use base 10, right, for numbers, and computers use binary. Now for binary, when you represent floating point values in binary, your representation is different, and it need not always be like a fixed number. Like if I remember correctly, 0.5 or something, like a very simple decimal, 0.2, 0.5, something like that. It becomes a recurring binary value rather than having like 0.5, one digit 0.5 when you represent it in binary. I think that becomes like a recurring thing.
It tends to make a mistake when you do any kind of arithmetic with floating point, where it'll end up with error at like the very end, like the very smallest value, because it's like there'll be some like bit overload.
Yeah.
It's just that.
Yeah. So this precision also affects like this is going more in the domain of applied maths or the actual algorithms that you're running. So if your algorithm is like, normally that's what we see in physics based of algorithms, that you need very heavy precision, otherwise you run into something called numerical instability, that instead of converging to a particular solution like with differential equations, you try to when you do it with software, right, with numerical software, you try to converge at a particular solution, and if the precision is not good enough, your algorithm can go into diverge rather than converge. And that's something, again, those mathematical floating point precision, what type of division, what type of rounding off thing. There's so many things that you can adjust. All of that is done with compiler flags. And we'll study some of that because there's some of it which it's always a balancing thing between performance and precision accuracy. Like, but depending on the application, we can sacrifice some precision and accuracy for better performance. So that's something that we do on compiler flags. Yeah. But yeah, now I think we should jump to we only have half an hour at least. I don't just want to bore you with theoretical stuff. But yeah, any other questions apart from what we covered today?
Like how old are the CPUs
In
Hummingbird?
I think it's 2015 timeframe CPUs. So pretty old.
And are they ever planning on upgrading it,
I
or
don't
is it good how it is?
I think it's good for them, like the task, the kind of simulations that they do, or for teaching, it's good enough for teaching. I think they have their own other clusters, more powerful clusters that they use for actual simulation and their genomic simulations.
And are those on campus?
Yeah. But I don't think it's accessible for us because did you take 148, Mark?
I took 125.
Okay. So did you work on Lux?
No.
Okay. So I
They
took
just
one.
gave us the option to use Hummingbird as
Okay.
our thing.
So there was one applied math course in spring on GPU programming, and we could access a supercomputer called Lux, which is again UCSC, but it belongs to the astrophysics department, and it's not accessible for everyone. But there you had all GPUs, so and very high-end CPUs. So for now, Hummingbird is probably this week and the next. After that, once the quarter is full on and everybody has an account on the Berkeley supercomputer, we'll switch there. So yeah, let's go on to some hands-on things. So is everybody on Hummingbird?
Yeah.
Okay. Please check if you can access this particular path /HB/home/NNEGI.
Well, it's your cruise ID.
Yeah, your name.
Yeah. I think you should be able to read it.
What's the command
Okay, let's see.
to like look at your
Do this ls /HB.
Yeah, okay.
Can you read this? Does this command execute and you get something like this? Yeah.
I don't get those things. It's just like a blank, like I have stuff in there, but it's otherwise.
You did PWD, right? Or what did you? What?
I did PWE and I did my
Yeah. Oh, I want you to access HPC basics from my directory.
from your drive.
Yeah.
Okay.
So just
Oh, I see.
copy this thing. Just run this command HPC basics.
Yeah, HP.
Yeah. Run this command.
CP copy.
Yeah, copy recursively from this location to your home directory. Kyle, Arshan, are you guys able to access Hummingbird?
Yeah, we were getting a permission denied.
Okay, so I'll change that permission.
Yeah, it's permission.
Can you retry?
Still denied.
Okay.
Get access to the fruit. Sudo, you run the command as root. So like if there's no permissions or something.
Yeah, so we don't get root.
Yeah, sad.
You're probably like set stuff on fire if we could.
Kyle, you don't need EduRoam. Like if you are off campus and if you're connected to the Cisco VPN client, then you don't need EduRoam.
Our secret. This is bioinformatics.
To get his
So you need to be on the VPN, on the campus VPN, so that. All right. I think this is working. Can you retry?
Yes.
Well, is it because it's in your directory? It's not?
Yeah, so I'm trying to make it read accessible. Can you try again? Okay, fine. We can still download stuff.
You can put it on GitHub and we can download it from that.
Yeah,
Or
I'll put
GitHub.
that. It's fine. Oh, here I can see this notification. Where am I getting permission?
Oh my gosh.
I'll do one thing. Just search for netlib HPL. So NETLIB HPL. And I think the first thing netlib.org benchmark HPL, a portable implementation of the high performance. Go to this and like right click on this copy link and just wget go back to your home directory and just wget and paste the link and press enter.
What's the website? Netlib.org.
Kyle, HP differentiates between campus networks. Okay, so one thing is, see, I can access directly if like I'm connected to EduRoam on campus, and I can access Hummingbird directly. But I think Aiden and other folks, when they tried, they had to go via Cisco. So are you using the VPN?
I'm not, because I was on campus, so I thought that it would work. I can set that up, I guess.
Can you try that, please?
Yeah.
It says on the
But it's
website that it works on
supercomputer
campus, but I've tried. I think it's like specific Wi-Fi places. It might be like here in the engineering building.
Yeah.
But like over by Kresge, it doesn't work.
So okay, are you all able to download the tar?
Yeah.
Awesome. So that's HPL. HPL stands for High Performance LinPack, and LinPack is like a benchmark that is for matrix multiplication, and it solves a set of linear equations. So once the download is done, you should have this, the red colored tar.gz in your directory. And yeah, so it's a benchmark written for matrix multiplications, solving a system of linear equations. And we use that to measure performance of systems. Like that's the benchmark which is used to rank supercomputing systems all over the world. And people have been optimizing this since, I guess it was launched in 1990s or something. And since then it is used every year. So this so there's something called top 500, which is the list of the top 500 supercomputers in the world. And this list is refreshed every like twice a year, once in June and once in November. And it coincides with the conferences that happen, the two supercomputing conferences that happen at the time. So in November, when we went to SC, which is the supercomputing conference which happens in the States, and the next one will be in June 2023. That's when ISC will happen in Germany. But like and this has been happening since when 1993. This list has been coming out since 1993, and since 1993 up till now, twice a year, every year, they run this benchmark on the world's largest supercomputers on all the nodes, and it stresses the nodes a lot because it's a very compute heavy benchmark. And that just we are going to run that. I mean, you can run this benchmark on your laptop if you want. It's a very tunable benchmark. You can define the problem size, and you can stress your computer. You can blow up your laptop. I mean, all depends on you. But we'll start our experiments with this thing. So once you have the tar downloaded, you can untar it with tar minus something like this, xf, and you can use tab is very good on bash system, on Linux system, because you can use it for autocomplete. So but this with this untars it, and you should get this HPL. You should get this HPL.23, a directory called HPL-2.3.
What does the Z flag do in tar?
So that's the GZ, because this is a gzip tar format. It says that use the gunzip whatever library to unzip it. So it's Z.
I use tar minus XF. Does that work?
No, so this is gzip, so it may not always work. Like it'll probably fail if you don't use Z. So X is for extract, and Z is if it was just a dot tar, XF is fine. But since this is tar.gz, it's ZX, XZ, whatever. You use both tags. So yeah, so you change directory, go to HPL cd HPL-2.3. And you should notice a directory structure like this. So this is like a structure of most HPC applications which are open source. Like you will have something like a file for the authors, a bugs file, a changelog file, some files which deal with how to configure the application that you're trying to compile, some make files. But the things that help us get started is the README. So I'm I have become comfortable with CLI based editing tools and like reading and editing tools, and I hope most of you are comfortable with that as well. If not, during these competitions you will get comfortable. So I use something like less to read a file. If you use Vim, Emacs, anything else like that, that's cool as well. But since I'm just looking for a read-only thing, so I open the README, and it gives you some, documentation about what the benchmark is, and it says, okay, if you want to install, see the file install in this directory. Is everybody able to read the README?
Yeah.
Yeah, awesome.
It's not that long, it seems.
Yeah. It's so we have to go. Let's check out the install file. So we go to install, and it gives you some instructions about how to build and run this benchmark. So it says retrieve the tar file. We already did that. We extracted it. Now it says create a make file, and you can reuse one contained in the setup directory. This make file contains the compilers and the libraries with their paths to be used. Okay, so let's go back. This is our directory. If you look into the setup directory here, it has some predefined make files. So is everybody familiar with what a make file is? Okay.
No, exactly.
So normally when you build applications, right, you use compilers. So do you remember, have you used a compiler to build an application?
Yes.
Yeah. So like a hello world. So if you write a C program, let's say I'll try. Let's say I write hello.c. This is and let's say I say in yeah.
You just do printf.
This is like a starter C program to just print hello. And once you have that, you say, so some commands that you should, like I may use it very, like I may not talk about it a lot, but if you don't understand any bash command that I use, just interrupt me so that. So now one thing that we use is which tells you, I say which GCC. So it tells you like I'm trying to use the GNU GCC, the C compiler from GNU, which is pre-installed on Linux, and I'm trying to see where is this compiler stored on this particular system, and it gives me some idea that it's a GCC 5.4 version. And to verify that, I'll say like GCC version, and it says, okay, GCC 5.4.0. Okay, I'll use GCC and I'll say compile hello.c and I'll say name it hello.exe. Okay, and the compilation is successful. And if I execute hello.exe, it prints hello world. But because I didn't put a slash in, it didn't put a new file. So if I modify that, I recompile, prints hello world and a new line. Okay, so now this is how you compile applications. Okay, you state what's the compiler, you state what's the source code, and you optionally give an output file name for the resultant executable. Okay. Now, in HPC, in any kind of application which is a bit more complex, you may have multiple files, being used. Like if you have a complex, let's say, a web client application, like a web server client application, you may have one file which is used to write the source code for a server, one file which is used to write the source code for the client. Okay, and you then maybe another file to handle how a client and a server interact with each other, so on and so forth. You may have multiple source code files. Now, if you manually go and it's pretty cumbersome to manually write, to compile each and every file, right? And then maybe you want to create one, like you may have dependencies like that. So you may have to link different files together, different executables together, and get the final executable. And as your program becomes more and more complex, these steps keep on going larger and larger. So rather than doing everything manually, you can define something called a make file, where you define all these steps one after the other. And you just execute the make file then, and it'll run everything behind in the background. So make file is like a recipe for compiling and building your application. So let's see. Let's go to that setup directory. HPL. Let's go to that setup directory and read the make file for make.linux and Linux Intel 64. So since we are on an Intel chip which supports the x86 64 instructions, let's choose this one. Setup make Linux Intel 64. And now when I'm reading the make file, it has some comments at the top. Now, yeah, it starts, right? Okay. So it says use this shell. These are some commands that it defines for use inside. It says this is the arch, the identifier for the platform that we are going to build the application on. It defines the directory structure of the resultant of the current directory that we are working on and the dependencies that it wants to build and use. If we are going to build with MPI that we talked about for multi-node communication, we can give directions for external libraries to use. We can set those paths here. If we are going to use a particular linear algebra library, we can define everything here. Again, there are many other things. If you want to use some other interfaces, if you want to use Fortran, C, so on and so forth, different things in Fortran, everything is defined here. And if I'm trying to build something, it'll include certain files, like so header files. If you are familiar with that terminology, header files is like you have predefined some sort of functions or definitions that you may be using across files. You can put it in a header file. Like if you remember the C code that we wrote, hello world, the top line was include stdio.h. So stdio is a header file which contains the definitions for handling standard input output, which is reading from my keyboard and the system or printing to the screen. Now that's a predefined header file which is available from C. And you can define your own header files, and application developers define their own header files for specific functions that are heavily used in multiple components of their code. And that's all. Like that's one thing that we are trying to that you can specify in the make file. You can include some directory. You can include some libraries that are pre-built, so on and so forth. Like it looks very complex because even though this application, the HPL application is so like the description is pretty straightforward, the ways to achieve it, like there's so many things that you can try out, so many types of compilers, math libraries, MPI libraries, different languages, C, Fortran, so on and so forth, different algorithms in those languages. That's what makes these competitions, and that's what makes HPC like, it's just a vast and explored territory. Everybody is trying their own thing, and that's how these make files become so complicated. But like, yeah, key things that maybe you should focus on for starters is something called CC. The CC field denotes the C compiler that you're going to use or that the makefile relies on. So by default, this makefile that we're looking at, make Linux Intel 64, is going to use something called MPI ICC. MPI ICC is the Intel C compiler. MPI ICC it's a wrapper around ICC which uses Intel MPI. Okay, so normally for a single node we will use ICC, and for multiple node we will use something called normally that's how it's structured. If it's like GCC, it becomes like MPICC if we are using something else. So
What is ICC again?
it's the Intel C compiler.
Oh, okay.
And MPI ICC is the MPI wrapper around it. But this is just a term to focus. We'll talk about it more next week. But Aiden, the compiler flags that you were talking about, you were asking. So see here, these are CC flags, means the C compilers that are being used. C compiler optimization flags that are being used. So O3 is one which is by default used a lot in HPC. It's like an optimization compiler flag. And behind the scenes, it runs a lot of optimization things. Static, it generates static things. Wall, WAL is warning wall. So no com check. There are many things that are being used here. It's also saying that use OpenMP. So yeah, these are the things that are defined here and useful to us. Now this ends the makefile, but okay, for now, let's see. So we have which GCC, right? Okay. So for now, let's say C equals GCC, CC equals GCC. And okay, let's just refer to install again. Install was saying make arch Linux whatever. So make arch equals Linux underscore Intel 64. And before that, since I'm not using MPI ICC, I just want to start with GCC. Let's see if this works. Let's see. Yeah, so it started building the application, but it ran into some issue. Okay. 47, 947. Says use these things. Try ICC, okay, let's see if I can plot it. Okay, editor is NKL root. And
So are you guys CS majors?
Yes. UCS major?
I'm applied math. That's pretty close.
Yeah.
Not to computer.
So you had to take a bunch of CS classes.
I actually don't have to anymore. It's just math classes that I have left.
Where'd you
I have
transfer from?
Pasadena City College. Like in LA. You guys, you're freshmen?
Yeah.
From the Bay Area?
Yeah, I'm from Bay Area. He's from middle of nowhere.
Oh, there you go. Go for it.
Do you know any of the cities in like far North California?
Not really. Is it
No,
north?
Mount Shasta?
Yeah, I do. Yeah,
Okay, I'm
I drove
about
through there.
an hour away from Mount Shasta.
Cool. That's a really nice area, like
Yeah.
Northern California.
Yes.
Very cool. You go to Humboldt at all?
I used to go there sometimes.
I have a friend who's from there.
Oh.
Yeah, he went to Cal State Humboldt as well.
Yeah, I was thinking of going there, but I like Santa Cruz better.
Yeah, it's a similar kind of vibe. If you're looking for like research work, Santa Cruz is the place to go for sure.
Okay, I'm running into some errors, but yeah, I think we are also out of time. But I'll try to fix this and put it on Discord. But like yeah, the idea was to like since people have access to Hummingbird now, maybe you could try yeah, your experiments on this with HPA. Let's see if there's make arch should make it.
We're using the Intel 64 makefile.
Yeah. I think something is. I'll see. I'll debug this and put something. But like, yeah. I think the key idea here was that at least you're familiar with the structure of HPC cluster, the terms that are normally used: node, socket, cores, MPI, OpenMP, compilers, this and that. So, but like, yeah, that's the idea. InfiniBand. If you're familiar with these terms, it'll make your life easier for reading like cluster documentation. So for the competitions, when you're accessing a new cluster for the first time and you want to understand how that cluster is designed, you need to know these terms so that you can read it and understand what it is. And like, yeah, some hands-on thing on Hummingbird. But like, yeah, we at least saw how the scheduler works and how the queue thing works. But hopefully by tonight, you'll also have some idea as to how to build an application and run it yourself. Okay, I think we can end for now. Any questions in the Zoom chat? Okay, well, I can end the call. Thank you, everyone.
If each node communicates to other nodes via InfiniBand, can they communicate with nodes in other racks via the same technology?
Yeah.
How are like the wires connected to? Because there's like a rack in one part of the room and there's another one in another. It's just, can you like walk through them, or is just tons of wires?
There are tons of wires.
That's cool.
So yeah, that topology is again, if you guys are interested, I can talk about that as well. But yeah,
Will we be able to go in the server room to see how it works?
I don't know about Hummingbird server, but there's a server room here in the second floor, and Scott has access to it, and he showed it to us last time. But if you all are interested, I can ask him if we can show it to us.
Yeah, I would be interested.
Yeah, we can just see a data center how it looks from inside.
Okay.
Yeah. I'll